One thing I will say, I've been working on getting the recordings to go through properly now. So I was trying to use the podium computer. It wasn't working. So I switched over to my laptop, and the last few ones have worked well. Please understand it's a recording of the lecture. It's not meant to be just shared with anybody. It's meant for you to review as you need. Okay. If you ever miss a day, hopefully I don't forget, but it'll be there for you. Okay. With that said, today we're moving on in our continued discussion of rates of change. So I have a problem here that kind of continues from where we were on Monday. So we have a function, and let's find the rate of change between f of 2 and then these three other given points. That's our focus here. Now, one thing I hope you see here is I chose 3 points to go from 5 to 4 to 3. What would be next? 2, right? So we're building towards that, okay? Now, one thing that we talked about is make sure we remember that when we talk about an average rate of change, we can use the delta y over delta x. But what we're saying is y2 minus y1 all over x2 minus x1. The rate part is because we're dealing with a fraction, right? So we have a rate because we have a fraction, and each of those pieces is designated to specific things. The change part is the subtraction. Right, so that's why we call it a rate of change, is just putting those things together. With that said, though, make sure you see you're going to have to evaluate the function 4 times before we can do any of these, right? So first thing to do is go find f of 2. One thing I did show y'all the other day, this is where I would say, hey, synthetic division can get that done quick. Not that it's hard to plug into a quadratic, so whatever way you're comfortable with, please use that. But remember, synthetic division is a great way to run through this and get that done. Just remember, it's going to be the remainder theorem here, right? So, f of 2, we couldn't use it for factoring purposes, but now we know we get 3 when I plug that in. Everyone follow me on that? Did everyone get f of 2 equal to 3 that worked out already? So with synthetic division, I brought down the negative one, then you multiply to get up. So that would be 2 times -1. That's where this comes from. Then to come back down, we had to do 2 plus -2. So that's where the 0 came from. And then remember, multiplication to get back up. So 2 times 0 is where this 0 comes from. And then 3 plus 0 is 3. Now, again, you may write your synthetic division differently than I do, and that's fine. This is just the way that is ingrained in my head, okay? With that said, though, hopefully you can see you can do that with all the values that we have here. So I could do the same thing over here with the 5. And to me, it's just one of those things that I like to always point out because it's a way to quickly get something done and hopefully build some confidence in the work that you're doing. All right. Did we get -12 though when we plugged in 5? Was there any concerns then with actually going through here and doing the work with the average rate of change? So we're all good with this one being -5 for the first rate of change we have here? Right. What's something we can take from that, right? Well, hey, there's no decreasing going on from one point to the next, right? So as we go from x equals 2 to x equals 3, my graph is decreasing. Okay, now we don't know, we could hopefully you have kind of a picture of this graph, right? We should be visualizing, hey, I have a parabola here. But what we're seeing is, hey, maybe I pick these 2 points like that. Because as I go from left to right, it shows a decrease taking place. Okay. Now, as far as the rest here, we can do those kind of through the same process. When we plug in f of 4, though, we get 5. -5, sorry. Oh, something was not looking right. My apologies. Should be -5, though. Okay. When we do the average rate of change for this particular problem, though, make sure you see it's -5 minus 3 all over 4 minus 2 now. So do we agree with -4 with that one? Any concerns with that? So now we got the last one here was f of 3. That one worked out kind of nice, right? And find that this equals 0. So do we agree with the rate of change being -3 now? Any concerns with that? Now, the one thing I will do with this is go draw a graph in a second. We kind of look at it, but are we good with the working out to get to these values? That's the first part I want to make sure we're comfortable with before we move forward.
You don't want to plug in.
Oh, you can. That's another way to do that. I'm just showing, this is me just making sure to show a way that could be when you have a polynomial function, it can help make it just be a little bit faster. If you plugged it in like -5 squared plus 2 times 5 plus 3 by hand, that's fine. Your calculator can do that as well. So in the end, I'm just trying to show a way that by hand can be done quickly. That's all. Okay. Another thing here, remember with limits, trying to find if something can be factored, this is a good way to do that, right? I can now give you a polynomial that is not a quadratic that, hey, I can use synthetic division. Just know it only can factor if the remainder is what? 0, okay? Any other questions though? All right, so make sure the thing that you're seeing here is that, hey, as I did the rates of change, I kept f to 2 the same, right? And I picked 3 points after it. All of them are still decreasing, right? But hopefully what you see there is the slope went from -5 to -4 to -3. Okay, so it's all still negative. But what we're interested in, hey, as I went from 5 to 4 to 3, I'm getting pretty close to 2 itself. And we're curious what's going on as I take an average rate of change and I try to get the denominator as close as I can to 0. Remember, we can't put 0 in the denominator, but we want to try to as much as we can. Each of these, though, is called a secant line. So if I come over here and do a quick sketch of the graph, I didn't mean to delete it earlier. So f of 2, well, we know this is f of 3, right? Because f of 3 was 0. Right. We could say that f of 2 is about right here. We said that was what, 3, right? Everyone follow me on that? Now, when I looked at each of these other points, though, make sure you see here as I went through here, I just picked other points to give us a way to compare what was taking place. Okay. So as we did this, actually, I did 4 and 5, huh? We had this point way down here, and we were showing that, hey, that has a slope there. But that's what we call the secant line, right? That's whenever we use an average rate of change, we can create a line that passes through our graph at those 2 points we focused on. It doesn't match our graph. It doesn't necessarily give us a perfect representation of what's taking place. But if we just needed a quick approximation, hey, this is great, right? Some of the application problems you'll see in the assignments and stuff going through this, it will talk about velocity, right? So if f of x is a position function, like you drop a ball, so it'd be the height of the ball as it falls, we could talk about the rate of change, right? So the height changes over the time changes. Well, that's like miles per hour, but it might be feet per second or meters per second instead. So it gives us a quick approximation of what's going on. What I want you to see here, though, what I wanted to do was to show you that, hey, as I come through here and I look at these different secant lines, the slope started changing. And eventually what we want to get to is not a secant line, but a tangent line. All right. What that means is instead of passing through 2 points on my graph and giving me an average, if we can get it to where we can overcome the 0 in the denominator, of course, that's the tough part we have to talk about, then not an average rate of change. Now we would have an instantaneous rate of change. Okay, and that instant rate of change would help open up everything we were dealing with from the mathematics perspective, because now we could talk about an object's not just position in a given moment of time, but its rate of change as well, right? So as we talk about velocity, well, if we could talk about velocity, that will open us up to be able to talk about acceleration. Now, that's a little bit tough to talk about acceleration from this graph, because as we're looking at here, we could do an average rate of change to get an idea of velocity, but we really need that instantaneous rate of change to be able to expand the focus of what we're doing here. Everyone follow me on that? Now, with that said, make sure you see here, though, two key terms that we need to watch for are secant lines and tangent lines, okay? A secant line gets connected to average rate of change. You have 2 points. We can do the rate of change just like we did with those previous one. A tangent line gets connected to the instantaneous rate of change, all right? Because what we're doing, as mentioned, I think someone pointed out, was just a slope formula, right? So if you go back to here, make sure you saw what I wrote here, we call the slope formula, but that was specifically for lines. We're not just doing lines here, right? We're looking at, in this case, a quadratic, okay? So with that said, the way that we want to handle this then is to say, hey, to get the instantaneous rate of change, what we want is the slope of a tangent line. Hopefully you see the connection here to a tangent line. What we need to be able to do that, though, is going to need the limit as h approaches 0, okay? And what we're going to say is f of our value plus h minus what we get when we plug in h. Now I'm using h right now, but make sure you see here, we were looking at 3, 4, and 5. So +1, +2, and +3 away from 2. H generalizes it for us, right? If you remember what we looked in class the other day, that means then all of this is going to be over just h. Sorry, not f of h. That's supposed to be f of 2, y'all. My apologies. So make sure you see here, I'm still doing the same thing. Y2 minus Y1 all over X2 minus X1. But when we looked at this, we talked about something like the difference quotient on Monday. Just remember when we talked about this one here, if you do X plus H minus X, that's going to give me just H. Okay. Now for this particular problem, just kind of show us that transition from a secant line to a tangent line, I picked f of 2 to be our focus. Okay, so that's why you're seeing here I'm doing 2 plus h rather than the x plus h. So right now we don't want just any tangent line. We want specifically when x is 2. Right. With that said, make sure again, just see here that 2 plus h minus 2 is where this h is coming from. I didn't just make that up. Okay, it helps to know that that's what it simplifies to right away. But what you'll see here is, hey, let me go find the one missing piece and try to simplify it, and then I might be able to evaluate the limit based on what we looked at in the past, as far as direct substitution, a table, a graph. One of those ways should help us out here, okay? With that said, how do I find f of 2 plus h? All right, we got to plug it in, right? Now keep in mind, we already knew f of 2 is 3 based on our previous work, okay? But be careful here with this because it has that h involved. Okay. We're plugging in an expression now, not just a number. So we have to go through simplifying skills rather than jumping straight to an answer. Okay. What was one thing that we do have to be careful of as far as simplifying here? Don't forget the negative sign. That's definitely something to always watch for. How do you handle 2 plus h squared? Yeah, 2 plus h times 2 plus h. Now, we've looked at it a couple times for the sake of time, so I can make sure to answer any questions as we do it. All right. I'm skipping some steps there, y'all, so make sure you're on your own. If you need to see where I got this new trinomial from, go multiply this out. 2 plus h times 2 plus h, okay? So make sure you go through that process of doing that. But you would get h squared plus 4h plus 4, okay? Oops, I sure did. Thank you for pointing that out. Yes, so thank you for pointing that. I totally just put plus X rather than plus 2X there. Okay. So make sure we make that correction. That will have a big impact on what we're doing here. Okay. Now, with that said, though, as mentioned, we definitely want to be careful with our negative sign here because forgetting the 2 means I would have didn't distribute here. Well, the negative you have to distribute as well. What you'll see is that negative will make it negative H squared minus 4H minus 4. Okay. Now, keep in mind, what we're doing here is just trying to find that first piece. Then we need to go subtract f of 2. Then we'll make sure we keep h in the denominator. What do you notice about combining like terms here, though?
Yes.
Yeah, that's kind of nice, right? That's not always going to happen. It's just because of the values I picked here. The 4s do drop out to 0 for us. But make sure you see you can combine the negative 4h and the positive 2h, okay? Why did I put 6, y'all? That's what y'all were talking about, right? Sorry, they fried my brain with linear algebra before I walked in here. All right. Is there anything else I have messed up here? All right, it shouldn't have been 6, y'all. I distributed the 2 too far. It should have just been plus 3 on the end. Which is very important, though, as I mentioned. When we go to do the limit part, it should work out nicely, as we saw with that linear function we did the other day. We also did a quadratic function. It kind of worked out nicely, right? So we're expecting that. Now, we're going to look at some other functions today that it's going to involve some steps, right? We know that, like, watch out for square roots. Okay, that would be one example. We're going to look at rational functions when those fractions involved as well. But that plus 3 is very important because what did we get when we plugged in 2? We got 3, right? So those matching up is something that should kind of be like, hey, that I wanted that since I'm working with a quadratic. Okay. Any concerns here after I cleaned up my own mistakes getting here? Now I'm going to shrink this down a little bit because now we want to go back to what we are working with. And this is going to be the instantaneous rate of change. So we have the limit as h approaches 0 of negative h squared minus 2h plus 3 minus 3 all over h. Okay. Now this is coming from a rate of change, which again, I called it a tangent line though, because it's instantaneous. Okay. And I'll do my best to keep adding graphs to visualize stuff like this. Now, hopefully, again, what you see there, once I put that minus 3 in, those are gone. But what do the remaining 2 terms have on them that are in the numerator?
Yes.
And both have h, right? So I can go through and divide both of those by h as well. Does everyone see that? Would it be okay if I go over here and say the limit as h approaches 0 of negative h minus 2? Now make sure you see I put parentheses around it to make sure to show that whole thing is a part of my limit right now. Okay. The fraction helped keep it all together, but now that the fraction's gone, I'm using parentheses to say, hey, the limit is being applied to that expression. Okay. Well, make sure you follow what we just did. We plugged in the f of 2 plus h since we found it. When we subtracted f of 2, the 3's dropped to 0, canceled out. And then both those 2 terms had h on them. Just be careful. Remember, it was negative h squared. So since this had 2 h's, when I divide out the h, I have 1 left over. Okay. Now, what's nice about this limit, though, once I simplify all that out? How would someone go about evaluating our limit? Huh? This is a situation where we could try direct substitution. Does everyone agree with that? We don't have anything in the denominator anymore, right? So we're dealing with a situation. Let me go just try plugging in zero and see what happens. Oops, not yet. Well, hey, that's kind of nice because when we do that, what do we get? Right? If I plug in zero, I get -2. What that means is though, when I go through all this work, the slope of the tangent line at x equals 2 is -2. Okay. Now, for us here, the instantaneous rate of change, we would just say like, hey, the rate of change we're focused on is the -2. Okay, so that would answer this question here with what we're dealing with that. Now, real quick, as we come over here, what do you notice about the rates of changes? We went from 5 to 4 to 3, and then when we did 2. Does everyone see how it decreased until we got there? It went from an average over a period of time to something that's more reflective that, hey, at that particular point, this is what the slope would be, okay, of a tangent line. Excuse me. Any concerns though with after I got through here dealing with our limit? All right, so some things to make sure we point out here. Understand what the limit is telling me. The H was how far from our initial point we're looking at, right? What we want to do is look at what happens as that difference gets really, really small. Again, we can't plug in H as 0, right? We can't do that. That's why we need a limit. But the nice thing about this is we're saying, hey, what happens as that gets so small that we can't even tell the difference between it and 0, right? So all the points in that area are going to help us out with pointing to something. The good news is, once I simplify it, I no longer have to look at that perspective of I can't plug in 0, right? And now we can when we get here. So as I look at those values, they get really small, we can say that, hey, as this gets really, really, really small, we're not going to be able to distinguish between the number we're looking at and the -2. So that's where the limit helps us out to say, hey, that instantaneous rate of change will be -2. Now, we didn't actually plug anything in to get to it, right? That's why the limit is important. Okay. From the beginning, we couldn't do it because H can't be 0. The limit allows us to then go around that, where, yeah, at some point we did direct substitution, but that's because we're working with a limit. That was the language that allows that to happen. Okay, everyone follow me on that? Any concerns with that process down here, though, again, before we move forward to another function? All right, so the next one then is, hey, what if I give us a rational function? Okay. This time we're looking at x equal to -3. So make sure you see here, our focus is f of -3 is another way to write that. Now, before I go through this, let's make sure we're comfortable drawing a sketch of this graph, okay? So some things that you definitely want to be watchful for when we remember dealing types of different types of functions is areas where we have restrictions involved. Okay, so for this function, what do we not want to have happen? Why don't we want to? What would it do? All right, it'd put us in an undefined form, right? Remember, the key here is though, if you allow the denominator to be 0, we run into issues. Okay, so this was one of those situations that I would say, hey, to start the problem, let's just go make sure we say, hey, the denominator can't be 0, but as it's Taylor, right? You say we can't use 2. Okay, don't use 2 on this problem because that would make the denominator 0. And that's not, we can't define by 0 because it's not defined. Okay, With that said, we can expand our knowledge of this graph by doing 4 limits, right? The main limits we want to look at first, the limit as x approaches 2 from the left of f of x, and the limit as x approaches 2 from the right of f of x, okay? Now with these limits, this is going to be a situation where you should expect to use a table. All right. So this would be a good review just to kind of go back and say, hey, if I'm dealing with this from the left of 2, then I probably could plug in 1.5, and let's do 1.99. Just kind of get a quick example of what that might look like. Okay. I definitely hope that you've been practicing your calculator, because plugging this into your calculator will make that process a little bit faster. Okay. So the reason I'm drawing the graph, though, this is going to help us visualize the tangent line. Okay. The reason I'm doing the limit is I have a possible discontinuity taking place. I can't plug in 2, so I know it's not continuous. The next thing we can look at is what's actually happening in the graph so we can describe the discontinuity. Okay. So with that said, we had 1 over x minus 2, and let's just plug in 1. Plug in 1.5, 1.99. Now I could always plug in more points if I wanted to, but what's happening to the output values here? Each of the y values I found, they're decreasing. Now, is it getting smaller, the amount it decreases, or does it grow faster? Does everyone see how that change increases as we go from 1 to 1.5, as it did from 1.5 to 1.99? The change in x value is roughly the same, right? Does everyone see that? But the change in the y value, pretty dramatic, okay? So what would we say about this limit then if it's just going to keep growing in a negative direction? This would be our negative infinity, correct? Is everyone okay with where that's coming from? What should we expect the other side to possibly have involved in? Probably infinity. Now the key is, hey, we could build a table though to see if it's either negative infinity or positive infinity, right? Now, if you remember from college algebra, we can say it's infinity kind of at this point, but the limit will allow us to confirm that. Okay. So just building another table here, just remember the right side would be like 3, 2.5, and 2.01. Okay. Hopefully we get some similar values, right? So I do that, I get 1, I get 2, and then 100. But the big difference is, even though the values look similar, they're all what? Positive, right? So we couldn't plug in 2, so we knew that it was not continuous there. But what type of discontinuity is going to be there? When the graph does this, I totally drew my coordinate plane wrong. What do we call that? You remember the word asymptote that we kind of talked about the other day? Sorry, what I want you to see is we cannot plug in the positive 2, right? So we could put a dotted line there. I did a highlighter on one of the other maps, but when we deal with a rational function, what we expect is, hey, if I can't use it, it's possibly a vertical asymptote, okay? So the discontinuity here is dealing with the vertical asymptote. That's what this proves to us, that, hey, I have a vertical asymptote at x equals 2, which means when I go to draw this graph, it's going to do this type of behavior. Did I plug in exact values to get that? No, but that's the type of behavior that we should expect to see, okay? With that said, the only point that we really need to plug in here is going to be the -3. Okay, so make sure you see here, the only point we need to plug in is -3. All right, but hopefully what you're seeing here is I know that I have this kind of behavior taking place. All right, the only other thing you need to do then is look at the end behavior of our graph. Well, what do we need to draw our limits for to get end behavior? So we picked two from the left and the right because we wanted to focus on this possible discontinuity, and we've confirmed that, hey, we have a vertical asymptote at x equals 2. That's why I can't use it. Okay. If I want to look at the end behavior, what my graph does is I go from one to the very edges of our graph. What should x approach to do that? Infinity, right? So make sure the left-hand side would be negative infinity, right? The right-hand side would be positive infinity. The nice thing about this is both of them kind of follow that 1/x pattern. So what did we say that the limit as x approaches infinity of 1/x will approach? It'll equal 0, okay? Remember, we looked at that table, or this would be a situation where, hey, if you recognize that, I don't think you need to draw a table because we've kind of talked about that, right? The same will be true for negative infinity, right? Because the numbers may be negative, but they're still going to be approaching 0. So make sure you see here, not only do we have a vertical asymptote, we also have a horizontal asymptote for our graph. So when I go look at this graph, I now have a good idea of what it's looking like on both sides. Now, if you need to improve your accuracy, yeah, go ahead and start plugging in X values and you can find exactly where they hit. But remember here, I'm just doing the graph so we can visually look at what this tangent line is going to be doing. Everyone follow me on that? So we got to review our limits of infinity, whether you get infinity or we use infinity for our limits. But now we have a graph to look at. So when we do that, what's the slope looking like about right here? If we were able to get an instantaneous rate of change, what do you think the slope is doing? So when you say constant, do you mean horizontal? Would that be a tangent line right here? This is gonna be a tough one, right? Because how many times? It looks like it only touched once, right? But when we talk about tangent lines, we want it to match what the curve is doing right there. Okay, as much as we can. So make sure you see here, how did I draw my line just now? It's slanted, but it's going downwards, right? So understand that, like when you look at this graph, like, hey, it's probably gonna have a negative slope. That would be one thing I hope that we can start looking at as, hey, I can do a quick check by doing 2 points and be like, that secant line would be negative. So as I get closer, the tangent line is probably negative slope as well. Okay. That's where the graph would be helpful. Did you have to do the graph to get that perspective? No, you did not. The graph here was just me wanting to make sure we look at the limits because we did that, what, Friday, and I didn't really do that on Monday. So I want to make sure to review that. Is everyone okay with that? With that said, what we do need to do, all right, I'm taking away this stuff now. What we do need to do is go in and recognize that, hey, I'm trying to find the slope of a line that passes through that point. Tangent means it's instantaneous rate of change. So to get that slope of the tangent line, I will need to go use that formula that we just looked at. Yeah, it says, hey, I want to find f of -3 plus h minus f of -3, oops, all over h. Now, since we got this picture in mind, we can go look at their graph because it is a little bit better than mine. just make sure that when we look at this particular graph, our focus is going to be on a point about -3, okay? Now, hopefully you saw from our previous one, we want to go plug these values in, but what you're going to find is this one, we're not going to be able to do as much. So this first piece, all I could do is -3 minus 2 and put it as a fraction still. So rational functions definitely are not going to be as nice to work with as polynomial functions. Now, we didn't have to do much with front end, right? Remember that polynomial one, we had to go do all this stuff here first to be able to move forward. So there's a little bit more work on the front end, but what you're going to find is we're going to have to deal with that fraction at some point, okay? Now, with that said, for f of -3, are we good if I put -1/5? Any concerns with that? Any questions before I move forward? Why I need those or what we're about to do with them? All right, so when you plug this in, be careful with your signs, of course. Okay, if we're subtracting 1/5, so you don't have to write it that way, but just be careful to remember, hey, I got to change this to a plus sign at some point. Okay, so if you're going to remember right away, just go ahead and put it as plus 1/5, but just remember it was subtraction. The negative is what made that addition just now. Okay. With that said, how do we bring fractions together? Because we have something that's called a complex fraction, fractions within a fraction, right? We don't like that. We want to get rid of the extra fractions. So what do I use to do the addition of fractions? In order to add two fractions, they have to have the same denominator, right? The good news is the only way to get a common denominator here is 5 times h minus 5, okay? The other thing that you're going to like here is we could just multiply the top and bottom by this, and it'll help me with the fact that I got fractions within a fraction. That'll eliminate the fractions in the numerator for me, okay? But make sure you see that 5 times h minus 5, I just took that from the denominators that I currently have, okay? Just make sure you see here the denominator, do not multiply it out. Oops. Leave this as 5h times h minus 5. Don't do that, because remember, we're going to hopefully be able to simplify after we do the addition here, okay? The other thing you need to remember, when I do this, I'm distributing to both of those terms that are in there already. So I need to multiply this twice, okay? Now for space, I'm going to take that tangent line. Remember, that's what we're looking for, though. With that said, though, make sure you see here, this would give us 5 times h minus 5 all over h minus 5 plus 5 times h minus 5 all over just 5, sorry, going too fast. All over 5. So when you do that distribution, you don't necessarily have to write this middle step out, but this will help kind of visualize what happens. So when we get this here, I distribute this to both my fractions. So 1 times anything is itself. That's where I'm getting that from. But what do you like about this fraction? All right, we're able to divide those out. Okay, we're over here, I can divide out those 5s. All right, make sure you see here, those divide out nicely, and this will set us up with something that doesn't have the complex fraction involved, okay? All right. What you'll see there, the first fraction just has 5 left over. The second fraction just has the h minus 5 left over. And that kind of looks like the denominators we've used previously, where those fives are gonna go to zero, okay? Which brings us to this place here, what happens to the h's? Doesn't that divide the one as well? So these fives dropped out because of the subtraction, the h's divide out, that will leave us with just a one in the numerator now. But at that point, that h by itself in the denominator, which was the issue from the beginning, is gone. So this is where we could say, hey, I know that this limit now can be solved by or evaluated by direct substitution. So we could say 1/5 times 0 minus 5. Okay, which is going to be 1/-25. Right? Now, at this point, what we're gonna have to do is say, hey, just make sure you see the process. I'm gonna pick up and do this again on Friday though, okay? So we can see it again. Not every problem is gonna be rational, but I wanted to make sure to introduce it today. But also make sure you remember from this, when I look at my graph here, we're trying to find a line that intersects the graph one time going through that point. That slope, if you look at it, it's only going down very little. Even the way I drew it is probably too steep. What you're seeing there, it goes down one and to the right 25. It's so shallow of a slope there. Okay. So understand what that 1/1 -25 is telling us is, hey, I can now find the slope of a tangent line. Okay. Now make sure you see here, this wants the equation of a tangent line. So not only will I review us going through this limit Friday, but no, we're also going to talk about how do I deal with the equation aspect, because all we got was the slope just now. Okay. Any questions or concerns as we finish up today? All right. Well, y'all have a good day and I will see you all on Friday.